the interaction cross sections, in particular, it can be also not only, so here I do show the proton-proton in square brackets because initially the analysis was applied for the proton-air interaction cross sections in this chat such a form, but in principle, both of them can be derived from the tail of the X-max distribution. And in the analysis, the assumptions are the following, that we do fit the last 20% of the X-max distribution, which is the proton-dominated tail. And in principle, this choice of the 20% was made in a way so we don't have the contribution from helium exceeding the statistical uncertainty, and any contribution of helium up to 25% will go then in the systematic uncertainty. Here you can see an example of the fit where there are two distributions. One is hydrogen and another one is helium. And like, yeah, the tail is being almost fully fit with the hydrogen tail. And then, so we can get this lambda eta values, which is analog of the attenuation length in the air. And then from the lambda eta values, we can get the interaction cross sections. For that, we first then need to construct the lookup tables, which will allow us to convert the lambda eta in the cross sections. And for this, the interaction cross sections are being rescaled with a certain linear scaling factor, which depends on the energy of interest, threshold energy, namely energy above which the modifications are allowed, as well as and then having this in place, we can put this in the air shower simulations and get the X-max distributions corresponding to these modified cross sections. It can be noted that these modifications are implemented for the Sibyl interaction model and the rescaling of the nucleus-nucleus cross sections, because here it's like shown for the proton-proton, so the corresponding rescaling of the nucleus-nucleus cross section is done via the Glauber theorem. And on this plot here, you can see an example how this rescaling would affect the nucleus-air interaction cross-section, for example. Here, the y-axis shows the ratio between the modified and non-modified cross-section, and x-axis shows the energy per nucleon. And the plot is shown for three different rescaling factor values at 10 to the 19 electron volt. That's the values are 0.5, 2, and 3. And one can see that with an increase in the scaling factor, the cross-section obviously rises, as shown from this plot, from this function. The largest changes are present for the hydrogen cross-sections, while the less changes for helium and even less for nitrogen, and iron remains most, not that much change compared to hydrogen. And since here the energy here shown per nucleon, so the onset of modifications is at the same point. However, in reality, of course, the onset of the modifications will be at the different energies. The heavier the particles, the later in energy the modification will start. And then, so having these modifications in place, we then can do the air shower simulations and get the corresponding X-max distributions for the modified cross sections. And here one can see the change in the X-max distribution shape as a function of the rescaling factor. In particular, one can see it's the example here is shown for the proton X-max distribution, and one can see that with the increase in the rescaling factor, we get the more narrow distribution as well. The X-max value gets smaller, and one can also clearly see how the tail of the X-max distribution changes with the change in the rescaling factor. And therefore, knowing the change in the lambda eta value, for example, for the different cross sections, we can then construct a lookup tables, which will allow us to convert lambda eta values in the interaction cross sections. So on this plot here, the changes in the lambda eta values at the function of energy is shown. Here it goes a little bit for the lambda eta values. The plot shows the values a little bit larger than the range where we have proton-dominated composition, and that can be also clearly seen that at some point around 10 to the 18.5 electron volt, the lambda eta values start to deviate significantly from the simulations for the pure proton composition shown in the green and blue lines. Therefore, in blue that's for Sibyl and green for EPOS LHC. And here the lambda eta values measured for the full phase 1 data are compared to the previous measurements of OJ, as well as also for the telescope array measurements. And in principle, there is like almost no difference compared to the previous results, so they stay the same. And then after applying this lookup tables, we then can do the conversion of these values into the corresponding interaction cross sections, which are shown here. The colors are the same. So in the dark pink, basically, the measurements from the data with increased statistics from the full phase 1 data is shown, and they are compared to the previous OJ measurements, as well as to the extrapolations from the LHC measurements, the corresponding interaction models like Sibyl, EPOS LHC, QGLZ. And one can see that, again, the cross-section values do agree with the previous measurements, as well as they do agree with all the extrapolations with all the hadronic interaction models. So, and in principle, as like that could be the end, because we have the measurement of the mass composition. We also have the measurement of the cross-section, which even so it works as shown here, mainly at the lowest energies where we have proton-dominated tail, but it still provides us the values above the LHC range, allowing to construct the interaction properties at the highest energies. However, there is a point that both quantities have a dependence on each other. In particular, that, as was said, for the estimation of mass composition, we do select one of the hadronic interaction models, or to use different hadronic interaction models, and the result differs depending on the chosen hadronic interaction model. As well as for the measurement of the cross sections, we do assume the proton-dominated tail of the X-max distribution with at maximum 25 contribution of helium. From these two plots here, one can see how the change by plus minus 20% in the Sibyl 2.3D cross-section will reflect in the mass composition. In particular, with an increase in the cross-section by 20%, we essentially would get the decrease in the essentially we'll get the decrease in the helium fraction at the highest energies and the corresponding increase in the nitrogen fraction at the same time. So that was for the decrease in the cross-section, and with the increase in the cross-sections, we then would get the reverse effect. And these effects are of the level, the same 20% in the fractions, especially at the highest energies. The lower energies, the changes are less, as well as hydrogen remain less affected. But that shows the importance of knowing the cross-section for estimating mass composition, and vice versa, of knowing the mass composition to be able to estimate the cross-section. And that remains a little bit of uncertainty in the analysis because we don't know both of these quantities exactly. And one of the possible improvements is to try to estimate them at the same time because of the already mentioned assumptions that for the mass composition, we usually assume a validity of certain interaction model, and that for cross-sections, we do assume a proton-dominated tail of the X-max distribution. And that can be done in the very easy way by fitting the mass composition using the model predictions with the scaled cross-section. So not fit only the tail of the X-max distribution, but fit the whole X-max distribution. And then just find the best fit combination of the fitted parameters. And the first attempts to apply this to the data shows that in principle, even by fitting the whole distribution, not only the tail, we still get the same cross sections. The fit is shown in the blue line here, where the shaded, dark shaded area shows statistical uncertainty and lighter area shows the systematic uncertainty. And so one can see that in principle, the fit obtained from the whole distribution also gives the same result. The fit obtained from the whole distribution when composition is considered also in the fit gives in principle the same results as a separate estimation of the cross-section. It also agrees well with the extrapolations from the low energy models. And that's the analysis that is still being in the process, and the more precise estimation of the uncertainties is of course needed, but that so far looks optimistic, meaning that probably we can get a little bit better estimation of both quantities. And that brings me to the summary that from the observed X-max distributions, we can derive both mass composition and the interaction cross sections. And the results with the full phase one data with increased statistics do perfectly agree with previous findings. We do get the same chance in the mass composition, and also the proton-proton cross sections agrees with the previous measurements, and as well as the extrapolations from low energy data. However, there is this point that the estimated mass composition do depend on the assumed hadronic interaction properties, in particular cross sections, and vice versa. Therefore, we need some improvements in the analysis of both quantities, for example, as the simultaneous estimation of both of them. And of course, there are also hopes for the further insights on both mass and interaction properties from other methods, such as deep learning, or also from the Auger prime upgrade. Thank you.
Thank you very much, Alina. So do we have questions in the room?
Thank you. Very nice. Is this analysis impacted by events migrating to different energy bins, and is this corrected for somehow?
Yes, the systematic uncertainty, like related to the events related to the energy, is taken into account. It's taken into account as an uncertainty in the analysis. So, like this is in the systematic uncertainty, we take into account that the events can be in the different energy bin.
Okay, and is this a big effect?
No, that's not that big effect. It's like the systematic uncertainty is not being dominated by it. It barely reaches probably like a couple of percent. But we do not consider the huge change in the energy. So that's only by half of the energy bin.